Throughout our astrophysics unit so far, we've really been focusing on stars and identifying their qualities and properties, as well as where they are in their life cycle. Today, we're going to zoom out a little bit and expand our topic to more of the universe as a whole rather than just the individual parts of that universe. Today, we're going to be talking about the science of cosmology. Cosmology is the study of the universe itself, not to be confused with cosmetology, which is something entirely different. So, just a review of the things that are in your data booklet, things that we have looked at and seen so far. We're going to be focusing on right now for this lecture, this subtopic D3 in the IB physics data booklet on cosmology. And you'll see that there's a bunch of interesting equations there. We're going to get into all of those today and for our next lesson. To start us off in this conversation, we need to talk about a very important person in science. Henrietta Swan Leavitt is responsible for a really huge breakthrough in our understanding of how the universe is functioning and ultimately expanding. Henrietta Swan Leavitt worked as a computer, is what her title was. If you've seen the movie Hidden Figures, very similar to that, that a lot of the calculations that were done in the past were done in rooms often staffed by women. And one of her jobs was to catalog different stars. And specifically, she was focusing on cataloging a type of star called a Cephid variable. It is a star that changes its brightness throughout its lifetime. And a Cepheid variable has kind of this cyclical nature that sometimes it's more luminous and sometimes it's less luminous. And it kind of in the night sky is twinkling over a period of hours, but mostly usually days. And one of the biggest things that she noticed as she was cataloging more and more of these is that the more luminous stars, the bigger stars, had a longer cyclical period to them, that it took them longer to go through these bright spots and dim spots versus just a smaller star cycled much, much more quickly. Because of that, she was able to build this relationship talking about how the period in days, the longer the period was, the more luminous that star would be. And as a whole, it sounds like kind of a cool observation, maybe an interesting pattern to find, but doesn't seem all that useful yet. The reason that that is going to be useful is one of our main goals in astrophysics is to try to find other properties of these stars. And we have gone through some different calculations and ways that we've done that. This is going to unlock yet another strategy for us. We're going to treat these Cephid variables as what we call a standard candle. I'll talk more about that term in a little bit. But if we think of a graph of the brightness of this star over time, and let's say that we find that this period goes from like 2 days to like 7.5. So it's looking like a period of about 5.5 days in between bright spots on that star. Now, if we know generally where all these different stars are landing on this graph, this relationship, all we need to know is the period, and we can figure out what the luminosity is going to be. Now, this was able to be figured out by finding the luminosity in other ways for stars that were close enough that we could use the distance from parallax angle or something that was on the HR diagram that we knew was kind of in that neighborhood. Here, we have a way of finding the luminosity just based on how long this period is for the star's brightness and dimness to cycle. So Cepheid variables with longer brightness periods are more luminous. The reason we can call this a standard candle is a standard candle is basically something of known luminosity. If we know how many watts it's outputting, we can actually figure out how far away it is because we can measure its brightness. So we can use the Cepheid variable to figure out its luminosity in watts. If we know the luminosity in watts and we can measure its brightness, we can actually figure out how far away that object is. A standard candle is just something that we know how luminous it is, so then its brightness can basically tell us how far away that it's going to be. So what this looks like with numbers is something like this. We say, what's the period of the Cephid variable with the brightness shown in the graph above? This is similar to the last one that we saw. This has a period of 5.4 days. We know what the brightness of this star is. So all we need is to know the luminosity, and we can work backward to figure out how far away it is. So if we know the period is 5.4 days, we can trace that up on our graph and figure out where it matches this line, this grouping of this is pattern. So 5.4 days looks like it crosses the y-axis here at around 1,500 times the luminosity of the sun. If we know the luminosity of the sun, we can figure out the luminosity of the star just by multiplying that by 1500 to find that the luminosity of this star is 5.76 times 10 to the 27th watts. So now we have the luminosity. We can use this relationship that the brightness is just the luminosity divided by 4 pi d squared, where that's basically just the surface area of the sphere that has a radius, the distance you are from the star. We can rearrange that to solve for the distance, and we get the square root of L, the luminosity, over 4 pi times the brightness. Plug in the numbers that we have, and then ultimately figure out the distance is about 7.57 times 10 to the 27th meters. So again, all we had to begin with was the cyclical period of this special type of star and the brightness of that star. From those two numbers, because of Henrietta Swan Leavitt's work that she started, we can go backwards and figure out what the distance this star is away from Earth. That's a pretty amazing thing. There is another type of standard candle that we can do a similar sort of work with. That's known as a type 1a supernova. This supernova forms when there's a white dwarf that's accreting matter from a companion star. So this is showing what that looks like. In our last topic, we talked about how there's a certain limit for how big a white dwarf can be. So what's happening here is there is a white dwarf that is nearby another star, and it's basically drawing in some of the matter of that star, and it's adding it to its mass. If that mass goes above that limit being 1.4 times the mass of our sun, it can no longer be a white dwarf and explodes outward in this really beautiful supernova. Now, this way of forming this supernova is a very consistent thing because it will basically add matter until it hits that limit. So that means that this explosion that happens is exactly the same every single time. And we've observed this happening many, many different places throughout the universe. And since it is always the same, it is a known luminosity. And as we saw with the Cephid variable, if you know the luminosity and you can measure the brightness from Earth, you can, from that measurement, figure out how far away this object is. So, before we get into talking finally about cosmology and how this connects to the universe, I want to remind you of a particular effect of waves that is pretty fascinating. It's called the Doppler effect. Where we are most familiar with it here on Earth is the Doppler effect associated with sound. Doppler effect is basically if something is coming at you, like a siren on a police car is coming at you, you're going to hear that siren at a slightly higher pitch because the wave fronts in front of that moving object are being squished together, which increases the frequency. Behind the siren, you are hearing that siren at a slightly lower pitch because those wavelengths are being stretched out behind the moving object. So if that ambulance or that police car is going by you, you typically hear it go wee 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 wee. So as it passes you, it has a noticeable change in its pitch. For this to happen with light, the object has to be moving very, very quickly. It has to be moving close to the speed of light to start seeing a difference. And this difference is seen not as the pitch of a sound, but rather the color of the light. Red light has a longer wavelength, so if the object is moving away from you, you're going to see that light at a slightly redder hue than you would normally expect to see it. If that object is moving toward you, you're going to see it more blue because blue light has a higher frequency and red light has a lower frequency. We call this redshift and blue shift. Turns out that a lot of the objects in our night sky are redshifted, that they are more red than we would expect them to be. Let's get into this idea of what I mean by expect them to be. Why would I expect a star to be a certain color? Well, it has to do with these spectral lines that we talked about a few lessons ago. As you may remember, different elements have this fingerprint, these different wavelengths at which they are emitting light. So if a star has hydrogen as part of it, or helium as part of it, we would expect to see certain lines at exact wavelengths that we know what they would be. And we know what they would be because we can do those experiments here on Earth. Now, if we look up in the night sky and look at some of these stars, we can recognize those fingerprints, but even though they're exactly the right spacing, they're shifted a little bit towards the red part of the spectrum. And we can measure how much that shift is and actually figure out how fast that object must be moving away from us. So when I say red shifted, doesn't mean that I look up at the night sky and I see a star that's just like super red to the naked eye. Instead, what it means is these spectral lines by the known elements that are in that star are shifted a little bit if you were to look at that star's light through a prism. We can calculate this redshift through this relationship here. Now, it looks like a crazy series of alien letters and symbols. So let's break down what these different symbols are representing. Z, in this case, is our variable to represent redshift. The value of Z isn't as important as this relationship here. So Z is going to be the same if you're talking about wavelength or velocity, but for now, we're not going to worry too much about Z itself. This delta lambda is the change in wavelength. It's how different those spectral lines are from where we would expect them to be. This lambda sub 0 or lambda naught is the wavelength that is emitted. So this is the essentially the original wavelength. If it were not moving, that's the wavelength we would expect it to be. And then v is the velocity of the source, is how fast that object is moving. And c, as you probably remember, is the speed of light 3 times 10 to the 8th meters per second, 300 million meters per second. This equation, this relationship is found in your IB physics data booklet. It shows up right here, the first equation in our cosmology subtopic. So we can calculate this. Let's see an example of it. A characteristic absorption line often seen in stars is due to ionized helium. It occurs at this particular wavelength, 468.6 nanometers. If we look at the spectrum of the star, however, we see this line, this known helium line, to be at a slightly different wavelength, 499.3 nanometers. What is the recession speed of the star? Okay, so the trick here is basically figuring out what to do with these numbers. There's clearly a difference between them. So if I take the difference, I know the change in lambda. I know the change in the wavelength. If I know the wavelength that was being emitted, that is this one here, I can plug that in. So the difference divided by the wavelength that we would expect it to be is roughly equal to the speed of light on the denominator with the numerator of the speed that it is recessing away. And that ends up being about 2/3, not 2/3, 1.97 times 10 to the 7th meters per second. So very, very fast, not quite as fast as the speed of light.